Cross-linked polyethylene, commonly abbreviated PEX, XPE, or XLPE, is a form of polyethylene with crosslinks. It is used predominantly in building services, pipework systems, hydronic radiant heating and cooling systems, domestic water piping, and insulation for high-tension, high-voltage electrical cables. It is also used for natural gas and offshore oil applications, chemical transportation, and transportation of sewage and slurries. PEX is an alternative to polyvinyl chloride, PVC, chlorinated polyvinyl chloride, CPVC, or copper tubing for use as residential water pipes. What is cross-linking? Cross-linking is the general term for the process of forming covalent or ionic bonds in relatively short sequences of chemical bonds to join two polymer chains together. Cross-links can be formed by chemical reactions that are initiated by heat, pressure, a change in pH, or irradiation. Properties of cross-linked polyethylene: low temperature impact strength, abrasion resistance and environmental stress. Cracking resistance can be increased significantly by cross-linking, whereas hardness and rigidity are somewhat reduced. PEX does not melt anymore, analogous to elastomers, and is thermally resistant over longer periods of up to 120 degrees Celsius, for short periods without electrical or mechanical load up to 250 degrees Celsius. With increasing cross-linking density, the maximum shear modulus increases, even at higher temperatures. PEX has significantly enhanced properties compared with ordinary PE. Cross-linking enhances the temperature properties of the base polymer. Impact and tensile strength, scratch resistance, and resistance to brittle fracture are enhanced. Almost all PEX used for pipe and tubing is made from high-density polyethylene, HDPE. PEX contains cross-linked bonds in the polymer structure, changing the thermoplastic to a thermoset. Cross-linking is accomplished during or after the extrusion of the tubing. A higher degree of cross-linking could result in brittleness and stress cracking of the material, while a lower degree of cross-linking could result in a product with poorer physical properties. Almost all cross-linkable polyethylene compounds, XLPE, for wire and cable applications are based on LDPE. XLPE insulated cables have a rated maximum conductor temperature of 90 degrees Celsius and an emergency rating up to 140 degrees Celsius, depending on the standard used. XLPE has excellent dielectric properties, making it useful for medium voltage, 1 to 69 kV AC, and high voltage cables, up to 380 kV AC voltage, and several hundred kilovolts DC. Preparation of cross-linked polyethylene. Various methods can be used to prepare PEX from thermoplastic polyethylene, PELD, PELLD, or PEHD. The first PEX material was prepared in the 1930s by irradiating the extruded tube with an electron beam. The electron beam processing method was made feasible in the 1970s, but was still expensive. In the 1960s, angle cross-linking was developed. In this method, a peroxide is mixed with the HDPE before extruding, the cross-linking taking place during the passage of the melted polymer through a long heated die. In 1968, the Siopoulos process using silicon hydride, silane, was patented, followed by another silane-based process, monosil, in 1974. A process using vinyl silane was followed in 1986. Other cross-linking. Peroxide cross-linking, PEXA, the cross-linking of polyethylene using peroxides, for example, dicumyl peroxide or ditertibutyl peroxide, is still of major importance. In the so-called Engel process, a mixture of HDPE and 2% peroxide is first mixed at low temperatures in an extruder and then cross-linked at high temperatures between 200 degrees Celsius and 250 degrees Celsius. The peroxide decomposes to peroxide radicals, RO, which remove hydrogen atoms from the polymer chain, leading to radicals. When these combine, a cross-linked network is formed. The resulting polymer network is uniform, of low tension and high flexibility, whereby it is softer and tougher than the irradiated PEXC. The same process is used for LDPE as well, though the temperature may vary from 160 degrees Celsius to 220 degrees Celsius. Silane cross-linking, PEXB, in the presence of silanes, for example trimethoxyvinyl silane, polyethylene can initially be Si functionalized by irradiation or by a small amount of a peroxide. Later, SiOH groups can be formed in a water bath by hydrolysis, which condense then and cross-link the PE by the formation of SiO-Si bridges. Catalysts such as dibutyltin dilaurate may accelerate the reaction. Irradiation cross-linking, PEXC. The cross-linking of polyethylene is also possible by a downstream radiation source, usually an electron accelerator. PE products are cross-linked below the crystalline melting point by splitting off hydrogen atoms. Beta radiation possesses a penetration depth of 10 millimeters, gamma radiation 100 millimeters. Thereby, the interior or specific areas can be excluded from the cross-linking. However, due to high capital and operating costs, radiation cross-linking plays only a minor role compared with the peroxide cross-linking. In contrast to peroxide cross-linking, the process is carried out in the solid state. Thereby, the cross-linking takes place primarily in the amorphous regions, while the crystallinity remains largely intact. Azo cross-linking, PE-XD. In the so-called Lubonyl process, polyethylene is cross-linked with pre-added azo compounds after extrusion in a hot salt bath. Degrees of cross-linking. A low degree of cross-linking leads initially only to a multiplication of the molecular weight. The individual macromolecules are not linked, and no covalent network is formed yet. Polyethylene, that consists of those large molecules, behaves similarly to polyethylene of ultra-high molecular weight, PEUHMW, that is, like a thermoplastic elastomer. Upon further cross-linking degree about 80%, the individual macromolecules are eventually connected to a network. This cross-linked polyethylene, PEX, is chemically seen as a thermoset. It shows above the melting point rubber elastic behavior and cannot be processed in the melt anymore. The degree of cross-linking, and hence the extent of the change, is different in intensity depending on the process. According to the quality requirement for pipes made of PEX, at least the following degree of cross-linking must be achieved. In peroxide cross-linking, PEXA, 75%, with silane cross-linking, PEXB, 65%, with electron beam cross-linking, PEXC, 60%. In azo cross-linking, PEXD, 60%. Cross-linking measurements. Cross-linking is often measured by swelling tests. The cross-linked sample is placed into a good solvent at a specific temperature, and either the change in mass or the volume change is measured. The more cross-linking, the less swelling is attainable. Based on the degree of swelling, the Florey interaction parameter, which relates the solvent interaction with the sample, and the density of the solvent, the theoretical degree of cross-linking can be calculated according to Florey's network theory. Two ASTM standards are commonly used to describe the degree of cross-linking in thermoplastics. In ASTM-D 2765, the sample is weighed, then placed in a solvent for 24 hours, weighed again while swollen, then dried and weighed a final time. The degree of swelling and the soluble portion can be calculated. In another ASTM standard, F2214, the sample is placed in an instrument that measures the height change in the sample, allowing the user to measure the volume change. The cross-link density can then be calculated. Factors influencing cross-linking rate. Polymer concentration, 30 to 60 pounds per 1,000 gallons base gel. Cross-linker concentration, 0.01 to 0.1%. Base gel pH. Rate increases at higher pH. Base gel temperature. Rate increases at higher temperatures. Chelate ligand strength. Stronger the chelation, slower the rate. Brine strength. Higher brine strength. Weaker the gel. Additives commonly used in cross-linking. Organometallics. Titanates, zirconates, borates used in O and G coatings. TAC, trialyl cyanurate trifunctional, used in rubber and plastic. Oxime, used in silanes, acrylic, such as NMA and NBMA, used in vinyl acetate polymers. Cross-linking can be accomplished by a wide variety of processes and with a multitude of additives. This relatively simple process can alter the product properties dramatically, with relatively low costs.